Quite a while ago, we kind of actually finished the main part of the lecture of both 7 and 8, and it had to do with energy. Let me put it on the board here to kind of get us started. Here's kind of the summary of what we had. The shorthand way of writing it is to say the energy at one point is the same at the energy at another point. Hence the phrase conservation of energy. And so we can see the energy change forms, perhaps. An expanded view of this would be to say the initial kinetic energy plus the initial gravitational potential energy plus the initial energy from the spring plus any additional energy / work done from an outside influence not included in our other terms could be added to there. Those will be the energy at some moment. I'll use the word initial, but initial doesn't always mean the starting of the experiment. It could mean halfway through the experiment. This is the energy at that moment. What is it equal to? Well, it is equal to the energy at another moment. I'll use the word final, but that doesn't necessarily mean the end of the experiment. And in fact, I bring that up because one of the confusions in today's lab where students do the conservation of energy is they're so used to hearing the word energy initial equals energy final that when the lab asks them to run an experiment and calculate the energy, they want to do just the beginning and the end. And that's not the point of the lab, as you will soon see today. You will calculate the energy when you start. You will do it a half a second into it. Actually a little less. I forget how quickly our data takes. Actually, I think it's 20 times a second. So you will measure the energy initially. You will then measure the energy 1/20th into it, 2/20th, 3/20th, 4/20th, and the experiment probably takes 2 seconds. So 40 times you will measure the energy. And the whole point is to see that it is always the same. And so, again, I'll use the word initial and final, but that's not exactly what is meant in all of this. It is meant the energy at one point is equal to the energy at another point. And so we'll just call it 1 point initial and another point final, but they can be anywhere. Well, I can continue on here because then we would have then the final kinetic, the final gravitational potential energy, the final spring, and the heat, and I guess I've been spelling the word heat out or writing out its equation. Maybe I'll use the word Q here because the traditional symbol for heat is a Q. I don't recall seeing it this early in the book, and so I'm not sure that the author uses the traditional symbol until we get to chapter 19, but he definitely eventually begins to do that. You saw me write this more in its spread out form, that this initial kinetic energy is 1/2 mv initial squared. The initial gravitational potential energy is mgy. The initial spring is 1/2 kx squared. And of course, the work is some integral of whatever this additional outside force, separate from springs and gravity and friction, are all about. And you'll see we'll use a couple of those today. And of course this equals then 1/2 mv final squared plus 1/2 gy final plus 1/2 kx final squared plus then the force of kinetic friction times distance traveled. And so that's how we worked it out, by doing those individual integrals, and it's been some time. So now I think it, at least I hope, it has sunk in quite well because we're going to wrap it up now. We're going to look at problems from chapter 8. We will spend most of the time doing problems from chapter 8, and now it's time to move into chapter 9. And obviously your test is coming up, and so Monday you will have your test on chapters 5, 6, 7, and 8. And obviously last time we did a bunch of problems from chapter 7. Now this time we'll do a bunch of problems from chapter 8. Then we'll get started with momentum if there's time today. If not, we will start the momentum on Wednesday, but we will definitely get started before your test. And then we will take the test, and then the following Wednesday, we will continue in Chapter 9. And hopefully get, if not all the way through it, very close, so that you will then have that time in spring break to go through Chapter 9. And then maybe even move forward into Chapter 10, both being the longest chapters of the book. I would encourage you to take advantage of that extra time during spring break to not only digest, but read these long chapters on there. So all of that is to say, let's go ahead and get started. A bunch of problems here listed. Let's see this conservation of energy principle in action and why it can be so valuable as a tool. I'll start here. It says a block of mass 0.25 kilograms is placed on top of a vertical spring with a spring constant of 5,000 newtons per meter and pushed downward so that the spring is then compressed 1/10 of a meter. Now, after the block is released from rest, it travels upward and then leaves the spring. To what maximum height above the point of release does it rise? All right, so like all of these, first thing I would always suggest is to pause, think through, read the problem carefully, get a good physical understanding of what is going on. So let's see, if I understood this right, the first part of it is to say that I have a spring in a vertical positioning. Unfortunately, the problem kind of spreads out over 2 pages, but the part that says it is pushed on top of a light vertical spring, that's the part that they are telling me. I've got a spring vertically. And so what's going to happen here is I'm going to come along then and place a box on top of it and push down. And so I will just call that mass little m. They, of course, give it in the problem as 0.25 kilograms is placed on top of a light vertical spring. Now, I should put up here the spring constant, K, is 5,000 newtons per meter. Okay, so there's my spring constant. And I push it down, and I don't think it says it on this page, but it said 1/10 of a meter. So on the next page, I can say it is pushed down by 1/10 of a meter. So here is the top, here is the bottom. That distance is 1/10 of a meter. All right? Then it says, after the block is released. Now let me put it right there, because they use that word release. I only point that out because the question goes on to say, what maximum height above the point of release does it rise? And I think the author could be a little more clear here, because he also said it goes up and it leaves the spring. You might call that a release too. Now, he didn't use that word, but I guess I need to ask you guys, what do you think he means by release? Do you think he means right here when my hand lets go? Or do you think right here where the block then is in no longer contact with the spring? I would call that a release. But he didn't use that word release. And because of that, I'm thinking he's talking here. Anybody else? The most important part of this discussion is let's just have a consensus on how we want to solve it. It's not really relevant on what the words are as long as we have a consensus on what are we after. Okay? It's early Monday. You need to care? No? Want me to pick it then? All right. So I will say that this is really the release point or the height of it, where my hand is no longer touching it. All right, so keeping that in mind, now we, I think, have a clear definition on what the question is, let alone solving the question. But again, he says, to what maximum height above the point of release? So what's going to happen here is the block is going to go shooting up into the air somewhere. And so that is really the question. How high from the point of release? Release being where my hand releases it, not the spring. And like I said, I'm just doing that because I think it's questionable, but like I said, he uses the words together, released from rest, and then point of release, does it rise? So picking that up as what I think is the question trying to ask. I probably should have looked at the solution manual, but then again, that's just the interpretation of somebody who wrote the solution manual, which is not usually the author of the problem. That being said, let's see if we can answer the question. But step one, right? Got a good physical understanding of what's going on? And so this is a good example of using conservation of energy. And again, that's what's going to be the hard part for you on the test as well as the final exam, and more so in the future as we learn more and more physical principles. Do you solve this problem with energy? Or do you solve this problem with Newton's second law, where we can do forces and accelerations? That's always a tough one to learn, and I think experience comes into play with that question. Obviously, we know since it's in Chapter 8, it must be a conservation of energy one. That's easy to decide. But like I said, on the test, it's not that simple. I will say this, though. One of the clues, not the only clues, and it's not like this clue always works, but one clue that I usually look for is, are they describing things in terms of distance, since work and energy is force integrated over distance, or are they describing things in terms of time? Because time would lead more to velocities and acceleration, which would be more appropriate for Newton's second law. And so that's kind of what I look for. And of course, this one, being in Chapter 8, clearly is listing things in terms of position. It clearly says it was pushed down 1/10 of a meter. That's position. How high did it go up? Again, that's position. So those are kind of clue words to you that the principle of conservation of energy is probably going to lead to the answer much easier than Newton's second law. Well, I know that Newton's second law is great, but it does involve accelerations. And I also know that non-constant accelerations are a little harder than constant accelerations. And that being said, I have a spring here. And a spring then gives different forces for different stretching or compressing of the spring. And therefore, this is probably a hard problem with Newton's second law. And it is. Not impossible to do, but it is a hard problem with Newton's second law. And hence, more of the same reason that I would say, I think this is a conservation of energy. And so that's the kind of thing I'm trying to convey that you're going to look for. Other than that, I think you'll see these problems straightforward, because remember, all of these little pieces were worked out from those long integrals we already did. I haven't really been using the word path independent or conservative force. But as you've looked through the book, you'll see that your author does use those words. And what he's trying to say here is you just need to know the initial and final positions of them. You don't need to redo the integral. We've already done them. And so I would say that anything that I come across a problem involving energy and gravity, I've already done the integral, don't do it again. I've done it for the springs, don't do it again. For velocities and kinetic energies, I've done the integral, don't do it again. Now, of course, other forces that come into play, we're going to have to do the integral. We got to ask what's coming into play. Heat, we've already done the integral, don't do it again. All right. So keeping that in mind, I think I can solve this one. I will start with one of these first questions, like, how about that term right there? How much initial kinetic energy does this have? 0, right? Why? It says it starts from rest. Speed is 0. Initial speed 0. Perfect. Next one. Initial gravitational potential energy. We had a long discussion about this already. It's worth repeating. Doesn't that depend on what you mean by y equals to 0? Yeah, and then we say this is the one where if you're going to use this equation, you have to call up positive, but you can still pick where you want to put y equal to 0. So I'll ask it, where would you like to put y equal to 0? Right, I'll go with release. I mean, like I said, I just want to ask you what you think is the better of options. I will say it does not matter. You can pick anywhere you want, and as long as you're consistent with it, I'll get the same answer. But I think calling the release point y equals to 0 does make a lot of sense, because the ultimate question here is how high is it from the point of release? So I might as well measure everything from the point of release. And of course, the other nice thing about that is if I call that point 0, then what is my initial potential energy? Gravitational potential energy. Yeah, that's 0 too. Good. So for two reasons there, I would think it is best to call y equal to 0 right there. I'll continue on here. How about this next term? What is the initial spring's potential energy? Maybe I should ask it this way. Where do you want to call x equal to 0? Yeah, don't let me fool you. You can't pick it, right? Right, that's the one we worked through. That's the one that was derived from Hooke's law. Hooke's law clearly stated 0 force at x equal to 0. And the only way you're going to get 0 force from a spring is when it's in its natural length. You don't get to pick the x anymore, right? If you're going to use that equation, you are deciding that it has been picked for you. As I so jokingly said twice, and one more time, you had that choice to get some sleep this semester, but you're not going to, given the choice of classes you picked to take. This being one of them. And so that's what happens here. I have picked that equation, and that equation has consequences with it, and one of that is where it was derived from, and where it was derived from clearly made x equal to 0. So I got to pick that. I mean, by picking that equation, I have also got to pick the natural length. And so there is the spring compressed 1/10 of a meter. So I can put in 1/2 times 5,000 times 0.1 and square it. And that is the initial energy. Of course, there is this term, there's nothing outside of the gravity or spring or heat or motion. Those are the ones that are already covered here. So let's move to this other side of the equation. What is the final speed? Yeah, again, it's 0. And I get that from understanding the problem. It's asking how high it goes. And so this thing is going to go up until it stops. Also notice this. And I tried to emphasize this before the first test, but some of you did it anyways on the first test. Do I really have to figure out how fast it is going here when it leaves the spring, and then figure out from how fast it's going there to figure out how high it's going? No, because this is one long problem. I can say the energy initial is equal to energy final, meaning the energy at some point is equal at the other point. Could I use an intermediate point? Oh, absolutely. I'm just making the problem hard and long, and as a consequence of that, I probably will spend too much time on it. And a consequence of that, I will probably not complete the test in the full way I would have liked to. And so you don't have to break it in two problems. Just like the ones from the last test, you shoot a ball up, you don't have to figure out how much time does it take to get to the top, and then how much time does it take to get back to the same height you fired it at, and then how much time does it take to get all the way down. From launch point to landing point, it's one problem with the same acceleration. And knowing that means I don't have to make the problem harder. Yeah.
So for the spring xi, it's a positive, even though the spring if the spring is being stretched to be a negative.
Ah, well, fair enough. Let's go back to that one. Remember, when we derived this, we used the equation of Hooke's law, and Hooke's law would be valid, 0 force at 0 position. So you seem to get that. However, notice Hooke's law is valid for any direction I call positive or negative. So I would say Hooke's law has not chosen which way is positive or negative. I'll illustrate. If I have a giant spring out here, okay, and I push it in, if I call that x equal negative, then the force comes out to be positive. On the other hand, Lost it altogether. On the other hand, thank you, if I push the spring in and call that positive, then I get a force that's negative. So this sign out in front, this negative sign, is not really choosing what direction is positive and negative. All it is saying is that the force is opposite to whatever you are calling x. And it works for whether you stretch it or compress it. So, fair enough, I should probably decide which way do I want to call compressing the spring. Shall I call that a negative or shall I call that a positive? Do you want to go with negative? Okay. Now, you're right, it's squared, which is why mathematically it wouldn't matter whether I call it the positive or negative direction, which just adds credence to my point that this equation in no way is defining which way is positive and negative. If you do define one way as positive and one way as negative, not a surprise, you end up with the same thing. So if it'll make you feel better to call down negative, because remember, using gravitational potential and energy, we must call down negative. So y definitely has to be negative on the way down. We make that choice when we use this equation. Just like we make the choice of x equals to 0 at the natural length once we use that equation. Again, that's why I think that people end up struggling so much in physics and mathematics and science classes in general because they really haven't looked at where these came from. You would never build a building and say, hey, I'm going to put a second story on it, I'm going to put a swimming pool up there. Well, what's the first story like? I don't care. I want a swimming pool. Does it matter how much weight you put on the second story? Right? What the first story and the foundation are built on are absolutely crucial. And so as boring as it seems to some to go through the derivation of where they came from, these are the things that end up with accidents. These are the things that make people crash. These are the things that make prototypes cost millions of extra money. It's the lack of understanding behind the equations. It's not just, oh, here's the equation, plug it in, get an answer. There's a lot behind it. And that's if you're lucky enough to even have the equation. If you're building something new, chances are very slim there's an equation. You've got to come up with the equation. You've got to come up with, based on the physical principles of the world, the own equation of how it's even been built. I mean, if there was already an equation, somebody already built it. And sorry, you're too late to make any money off of it. Okay? And so that's why we always get down to what are the fundamental physics? What can and cannot happen? All right, well, moving along here, then, and a good question on the positive and negative. Let me jump over to here. You already answered this since we're going all the way to the top. The final speed is 0. What about this one? Yeah, that is the number we are looking for, right? How high up did it go? I can put in the mass, I can put in the value of g. How high did it go was the, and is the question right there. What's this term? 0, right? The spring has now returned back to its natural length. And then how much heat or rubbing went on? I would say 0 there too. And so hopefully you're getting to this spot, and by the look in some of your eyes I can see you're already there, that yeah, this is pretty straightforward. This is, hey, punch in the numbers. If you understand the numbers, really it is just algebra. No calculus involved. Calculus has already been done for you when we worked out those equations. So one side of the equation is 1/2 times 500 times 0.5 squared. If I then divide that by 0.25 and divide that by 9.8, this comes up with 10.2 meters. And so there's how high it goes from the release point, which is also another way. If we take away 1/10 of a meter, it is 10.1 above the top of the spring, now that it has gone up. All right, well, like I said, hopefully that made somewhat sense. Maybe now we'll go a little further. In fact, this is a good one to do, number 7, because it is identical, well, almost identical, to the one you guys are about to do in class today. And maybe I should say part 1 of the one you're doing in class, because you are going to run an experiment here. And as I was alluding to earlier, what you're going to do in lab is you are going to measure the energy every, I believe it's 20th of a second, for about 2 seconds-ish. And then once you measure your data, you'll use that to calculate the energies and you'll plot it. And hopefully what you will see in the lab is the energy is the same, it's the same, it's the same, it's the same. Even though things change, like how high they are, so their gravitational potential energy changes, and how fast they're going, all of those change. But what you will end up seeing, being the point of the chapter, is the principle of conservation of energy. And our first experiment that we do looks a lot like this here. We have one mass up near the top of a pulley and a second one down on the table, and we let them go. And as we let it go, you can begin to see what happens is this one, as it goes down, goes faster and faster and faster, hence its kinetic energy is changing. It goes lower and lower, hence its potential energy is changing. This one here goes up and it goes faster and faster, so its kinetic energy is changing. But it goes higher and higher, so its potential energy is changing. And your job is to add up all 4 of those energies. Kinetic and potential of one object, kinetic and potential of the other object. And what you will see when you figure out what all those energies are and you add them together, you will see they will not change anywhere in the experiment. You will measure it here, 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 here. In our case, our problem's a little bit different. Number 1, we will not lift it 4 meters above the ground. We will just do something about this high, and so we will have about a half a meter off the ground. Likewise, we will not use such large weights. But the biggest difference between that one is this problem is just initial here and final all the way down at the end. We won't try to calculate everything in between. But like I said, the lab is to illustrate that you could do everything in between if so needed. Oh, there it is. Now, let's read this one here together and then start working it out. It says here, 2 objects are connected by a light string that passes over a light frictionless pulley as shown. The object of mass 5 kilograms is released from rest. A, determine the speed of the 3 kilogram object just as the 5 kilogram object hits the ground. Okay, well, let me keep this long equation around here. And let me apply this to that problem. All right. Let's start off with this. What is the initial kinetic energy? 0. Why? Okay, they say very clearly it starts from rest, right? Now, careful here. Aren't there 2 objects, though? All right, so I grabbed this one like the before, is that even though we write it up here as kinetic energy, we really mean this is the total kinetic energy. So obviously if you have one object there, you got to include also the second object. But what is the second object doing? Yeah, this is back to what we did back in chapter, I guess it was 5, where we looked at some pulley motion. And as this one goes down, this one goes up. Doesn't when this one go down 4 meters, this go up 1 meter? Isn't there a 1-to-1 ratio here? Which means, don't they have the same speed and the same acceleration? You remember doing those problems in chapter 5? So I would argue here that if this one is starting at rest, isn't that one also starting at rest? So I don't know if this will help, but it's kind of useful to put in your notes here that I am adding up the kinetic energies, and I'm doing both objects, they just both happen to be 0. So 0 plus 0 would kind of be my first step here. As I jump over here to gravitational potential energy, I would need to ask that first question. Where do you want to call y equal to 0? Yeah, right, and keep in mind, there's no right or wrong choice here. We still have that freedom of choice. But we have to be logically consistent along the way once we make that choice. Which is why if you're going to use this equation, what has already been chosen is up is positive and down is negative, but you can still choose y equals to 0. That's what we need to know. And I can pick y equals to 0, and I would think that one good place, certainly not the only one, is how about the ground there? And so if I pick the ground as y equals to 0, and measuring things from the bottom of the weight, then what would I say about the height of object number 2? 0, right? And so there's a 0. But what about the other one? The 5 kilogram. Then isn't it at a height of 4? And so as I kind of look at this, maybe now it's beginning to sink in. And as you get more experience with this, I would, of course, suggest you don't bother to write out the 0 and the 0 and the 0. You just realize, look, they're not moving, no energy there. One's on the ground, no energy there. But the other one clearly starts up in the air. The one obviously has some initial gravitational potential energy. And of course, like you guys in lab are going to have to do here today, is you're going to have to make a little formula in your Logger Pro. You're going to have to say, okay, what is the height of the object? And how is my equipment working to measure that height? And so you're going to have to figure out that as time progresses, the height that's changed. And so there's got to be some kind of data column that I get from my measurements that we'll put there. But for us, we'll just do a straight calculation. That's what it starts at. And then it goes all the way to the ground here. And I really like the way the author words it. It's going to make you think about it here quite heavily here. It says, determine the speed of the 3 just as the 5 hits the ground. All right, so why don't we start with kinetic energies on this side, final. Let's talk about the 3. Is the 3 moving? Yeah, so there would be a 1/2 m, whoops, and let me put in the value. It would be a 3 for its mass, and then it would be some final speed. How about the 5? Is the 5 moving? Yeah. Oh, I did. Thank you. Half. Got my 3's confused. Yeah. 1/2. And so I love this next question. Really come to a full understanding of this equation. What's the speed at this moment of the 5? Is it 0? Which I hear a couple of you say. Or is it the same speed? And I know some of you are saying 0, but why are you saying 0? Well, because it hits the ground, right? But if it hits the ground, don't I have to include this term? And we didn't, did we? Because wouldn't I be getting some kind of other additional force beyond gravity and springs and heat if I include the collision on the ground? So I'm not saying you can't include the collision on the ground. And if you do include the collision on the ground, then I agree that the speed is 0. However, I would also say then, for that problem to be complete, you must also include the force from the ground. So let me avoid that. I don't know what the force is on the ground, and I don't know how much distance it does to impact the ground. So let me talk about, what about the moment, just microscopically, what you guys have learned in your calculus, an infinitesimal distance above the ground. Maybe I'll call it a micron, but if you think that's too big, then let's go to a nanometer. And if you think that's big, then go to a femto. You get the idea, right? So maybe I should have done pico before femto and alto, you know. But you get the idea that there is a small distance, smaller and smaller and smaller and smaller, up to the point that I would say it hasn't hit the ground. And because it hasn't hit the ground, I do not need to include this. But also because it has not hit the ground yet, I need to say that it is moving. And as some of you pointed out, it is moving with the same speed as the 3. And so there would be my first two terms. They both have a, excuse me, a kinetic energy, which is why then when I come to the second term for the gravitational potential energy, what would I say about the 3? Hasn't it gone up to a height of 4? So I would say then that this one up here now has some gravitational potential energy. And of course, the harder one to discuss here, but maybe you see it now, is what would be the gravitational potential energy of the 5? It would be 0. But you say it hasn't hit the ground. Well, no, but how high above the ground is it? And this is my calculus, right? I can take an infinite limit getting closer and closer. And of course, eventually you would say, look, if this was 10 to the negative 99 or a googolplex from the ground, right? It is extremely small, smaller than my calculator can handle, and then I'll put a 0. And so there is the 0 height of it. And there's no springs involved in this problem. There's no friction or heat involved. And so, as you can see, like the other problem, it's just algebra at this point. Maybe before I grab my calculator, I'll even simplify this. The nice thing about them is they were like terms. So this is 1.5 plus 2.5, which gives me 4. And so over here, I can go 5 times 9.8 times 4. Over here, I can go 3 times 9.8 times 4. Over here, then, I can divide by 4. And then I can take the square root of all of that. And so 4.43 meters per second would be the final speed for that case. And it goes on. It's going to make me think more about this problem. I like it. Now, find the maximum height to which the 3 rises. Okay, so what happens next? Maybe a picture is worth drawing here, because at this point I have the 3 kilograms 4 meters above the ground. And I have the 5 kilogram microscopically above the ground, but soon to impact the ground. So what will happen next? Well, I suppose if I look at the 5, you know it will hit the ground. And as you pointed out then, what's its speed going to be? 0. And where did that kinetic energy go? Wouldn't there be some rubbing going on as we make impact? Let's say it's soft dirt. Wouldn't it kind of slide into the dirt? And so, isn't that what this term is all about? Now you may say this is solid to solid friction here, but maybe that's what I have, right? I have dirt, if you want to call that a solid, and I've got the piece of metal, if this is a piece of metal, it will be in class when we do it, and I can slide into that. So I would say that that energy goes here. What happens to the kinetic energy that's here? Well, exactly. It goes on up. The string itself, of course, probably becomes very loose. But it does continue on up because it has that speed. It has that kinetic energy. And like any object going up, as it goes up, it's going to lose that kinetic energy, but then gain that potential energy. And it's not going to keep going up forever and ever and ever. At some point, it'll give up all of its kinetic energy and its speed will now have stopped. And now it will begin to fall. But that is this question, or at least part of the question. Did they say how much additional height or total? Well, they say maximum, so I think they want to include the 4 plus whatever additional beyond that the 3 goes. So I would say that what we did in A was good, but I might kind of change my focus in B, where my focus will stop being looking at the total energy and just one of them, because I would argue that they're not connected together anymore. And that whatever energy this one has becomes, or kinetic energy that this one has, becomes the potential energy of this one. And so I can solve this problem, I think, a little bit easier by just looking at the energy of the 3. And that way I can avoid this whole question about it colliding into the ground. I can kind of separate it now into 2 pieces. How much energy does this one have? How much energy does that one have? And the string now between them is loose. There is no movement or flow of energy from one to another. So with that in mind, I'm still going to put initial energy is equal to final energy, but my focus now is going to be a little different. My focus is going to say what I mean by initial is right at the impact that the 5 makes with the ground. And when I start adding up these energies, it's not going to be the whole object made up of 2 pieces, but just one object. And so I would say then that this object then has a energy of kinetic of that much. That's what we just figured out in step A. There is the kinetic energy. And then it also has what's its height? 4. It also has some gravitational potential energy. And so measuring from the same location as before, I could have changed that, but why? I don't see an advantage of changing it. They're asking for its ultimate total height anyway, so I might as well measure everything from the ground, and I have already been doing that. But I do know then that when it gets to its top at highest point, what is its speed? 0. And so then I can write down as 3 times 9.8 times y final. So again, fortunately for me, most of this work has already been done in terms of the integral, and now I can just plug in the numbers and it'd be more of an algebra problem. And so 1/2 times 3 times 4.43 squared plus 3 times 9.8 times 4, that's the total energy there, divided by the 3 and divided by the 9.8. Oh, bummer. Let me go back. I hit a wrong button there. Instead of saying plus, I did times. Okay, so let me take that and divide it by 3 and divide it by 9.8. 5 meters. Good. First answer I got just didn't seem quite right. I got 150 meters. Like, I don't think so. So looking back at the formula, I actually hit a times key instead of a plus key right there. But anyways, I think you, and I hope, see the idea. And again, let's keep trying these. I hope they get to the point that you begin to go, yeah, this is kind of the same problem again. You're just saying initial energy equals final energy. Exactly. And if you get to that point, you begin to realize what we're trying to say here, what physics is. Physics is about knowing how to apply a few powerful fundamental concepts to explain the universe. And so that not only can you explain what is happening, you could go out and do something that hasn't happened yet. And you can use these basic ideas. You don't don't need a formula already given to you. Like I said, things that have not been done, we don't have the formula for them. You are going to build them. All right, well, I think 12 is a good one. I think each of these get a little progressively harder, but we've got that double Pulley system again that we saw back in chapter 5, the one that gave us such a hard time, that we're going to revisit here. But we're going to revisit a little differently, because last time we did it in terms of forces and acceleration. Now, let's view it in terms of energy. Although, as you will soon see, you can't completely answer this without first knowing a little bit about Newton's second law. So we are going to have to go back to chapter 5, which is part of the reason I think it makes a good problem. We get to review that tough problem, and we get to review chapter 5, which is what you should be doing in your studyings as you are getting ready for your test. But what did I say this was? 12? Number 12. Let's read it. Let's draw pictures. Let's talk about it here. All right. It does say review problem. It says the system shown here in 12 consists of a light, inextendable cord, a light, frictionless pulley, and blocks of equal mass. All right. So here's a good picture. Cord comes down, goes around this pulley, goes up around that one. And the cord, they're saying, it can't stretch. So the cord stays the same total length. All right. It is initially held at rest so that the blocks are at the same height above the ground. Now, initially. Okay, so I guess the picture they're showing is what I would call the initial condition. And so maybe somebody's got their hand under both of these. Find the speed of block A at the moment that the vertical separations of the blocks is h. So in other words, what happens if I let go? What if I put my hand under both of these blocks and I let them go? They're the same mass. Do they stay there? And if they don't stay there, do both of them go up? Do both of them go down? Does one go up and one go down? I mean, what happens here? Well, let's start with this. Do they stay there? I would say no. Now, they're the same mass, but why would I say no to that?
Probably boring otherwise.
Well, it would be boring otherwise. But I was looking for something a little stronger than that. Yeah.
Two pulleys.
Well, it does have to do with the pulleys.
Weight distribution is lighter for one than it is for the other.
Shall we do a free body diagram? Let's go back to chapter 5 here. Let's do a free body diagram. Let's look at block A here. Talk to me. What are the forces on block A? All right, tension pulling it up, gravity pulling it down. Fair enough? Let's look at block B. What's the free body diagram of block B? Exactly, that's the difference. There are two tensions, right? That's why it's a review problem here. But we've got tension up and tension down, and we've got gravity pulling it down, mg. And so what this pulley has done is essentially take the tension in this string and force it kind of wrap around, if you will. So the net effect here is this string is essentially pulling twice, if you will, on this block. And again, we saw that same thing in that movable pulley one that we did in chapter 5. And so this is exactly that same thing. But keeping this in mind, you will then, I think, see that the upward force on block B is more than block A, right? So they don't have the same upward force. Now they have the same downward force. They're each of equal mass. But what all does that mean? Well, will they both go up then? What would be the problem with both of them going up, and for that matter, both of them going down? Yeah. I mean, down, as you guys laugh, is silly, right? I mean, how can these possibly go down? What's gonna happen if they tried to go down is the string would have to be longer, right? And so that's ruled out. And how about going up? Yeah, now the string's got to get shorter, or there's no more tension left in the string, which is the whole point. They would be going up, and so the string would get all twisted and curly-cued. So just looking at the picture, I know they both can't go down and they both can't go up. But they could one go up and one go down, right? I mean, let's just say that block A goes down. I'm not saying block A does go down, but let's just say it does. If block A goes down, then what would that do to B? It's got to go up. All right, so I see how we could have one A go down and B go up. What about the other way around? What if B went down? Now, again, I'm not saying B does go down, but let's say it did. What would happen? A would go up. So those each make sense. That's the only way the string can stay taut and have the same length, is if one goes up and one goes down. I get that. That's a good picture in my mind of what is happening here. Now, maybe this picture will help me answer which one goes up and which one goes down. Well, doesn't B have more force on it? I mean, if any of them are going to go up, isn't it going to be B? And I think because of all of that, I could come to this conclusion, that two tensions must be greater than mg. You see, well, I shouldn't even put equal if it's going to go up. If it's going to go up, two of the tension, twice the tension's got to be more than mg. That will lift block B up. Now, that being said, also, if mg is greater than the tension T, then block A will go down. And I don't think this is a tension problem. It wouldn't be in this chapter. So I'm not going to solve this for tension, but just to help me with the understanding, I clearly know that the tension is somewhere into this category here, where if I want to write it this way, that the tension, right, I think I wrote that backwards. I did. That's not going to work. Let me fix that. Okay, so the first one is telling me that 2t is greater than mg. And the second one is telling me that the tension is, here's where I got it backwards, tension is less than mg. All right, so a tension less than mg is going to bring A down, and two tensions is going to lift it up. And I don't know, again, if it is really relevant here, but if I take 1/2 of mg, I can see that this one is saying the tension is greater than half the weight. But this one has already told me that the tension is less than mg. And so put those together tells me that the tension here, as this one says, is greater than 1/2 of mg. And this one tells me that the tension must be less than mg. All right, so that's what I know so far. Not that, like I said, that's even going to be real important to calculating the energy, but it is at least important to understanding of what is going to happen. And so maybe I'll draw a new picture, because that picture over there tells me what happens before I let go of it. Now I see that block A is going to go down, and block B is going to go up. And so I guess my drawing now looks like that. And what they want me to do is to say if those have separated by h, and there's the problem, right? Find the speed of block A at the moment that the vertical separation of the blocks is h. And so now, what is their speed? And in fact, to help me with my own clarity here, I probably then should put a line on here. Where did they start? And again, more reason why this is kind of a review problem here. Does block A, now that we've decided block A moves down and B moves up, do they move up and down the same distance? Right, they don't, right? Well, we're back to that, again, physical picture here, saying that, okay, if this would say go down 1 meter, in order for it to go down 1 meter, doesn't it need 1 meter of string? And where's it going to get that 1 meter of string? Well, the fact that this went up, we have the need of less string going down. But how far up does it have to go? Does it go up 1 meter? It only goes up a half a meter, right? Because if this, was up here, then this part of the string and that part of the string would not be needed here, and so that's why it can extend out and make that go down 1 meter, so that would be a half a meter. So maybe up here I could put the R for A and the R for B and say, all right, how are those two related? They're not equal, are they? The distance that A moves is, I think you said it right, twice of what B moves. So how do I put that into equation? Isn't that how I write it in an equation? That how much does A move? Well, A moves twice the amount that B moves. Although I'm also a little bothered by that formula, because doesn't that treat them both as positives? Now, maybe you're happy with that. I mean, you have that freedom of choice. You can choose to call one going up positive and one going negative. But remember, what did we do over here with gravitational potential energy? Yeah, didn't we already make that choice of calling up positive and down negative? And so if I'm going to come back over here and use the equation for potential energy, I need to be more consistent with my equation of up being positive and down being negative. So if block B goes up, then block A goes down. Maybe that's a better way of describing it. And if I take the derivative of both sides, I would get negative the velocity at A is equal twice the velocity at B. And so not only do they move different distances by a 2-to-1 ratio, they move by a different speed of 2-to-1 ratios. And again, we did this problem in chapter 5, and so that's why it says on there, review problem. But now I'm going to apply this to the energy discussion that we're trying to have in this question and answer what they said, which is how fast is block, and which one are they asking for? A. Find the speed of block A at the moment the vertical separation is h. So let's do this. Let's start by saying initial energy is equal to final energy. And initial energy would be in this picture right here. And I'll start with the idea that I have two boxes, and each of them I can talk about their kinetic energy. So for starting, how much kinetic energy do I have? Yeah, and maybe for completeness, I'll just put 0 plus 0. I've got 0 kinetic energy of the first block A and the second one B. What is their gravitational potential energy?
Initially 0.
Now why do you say 0?
Well, if you put equilibrium, it's begin.
Okay, so I need to make a choice here, right? Like all these problems, where do you want to call y equals to 0? We need to make that. And I think by writing it on your paper, make it very clear to yourself so you don't get yourself confused later on. Where would you like to call y equals to 0? And I think what you're saying is the starting point. I've got no objections to that. I just want to make sure that we all realize we're on the same page here. We all have that freedom of choice to choose it, and you can make that choice. So by your definition, and I'll go with yours since you were the first to speak up here, is I am basically saying they start maybe right about here in my picture. Because as we said, this one goes down twice as much as that one goes up. And so taking that as y equals to 0 means then that each of them start with 0 height and 0 potential energy. By the way, it also means that block A going down has negative potential energy, a discussion we had last time. That is okay. And we're even going to take advantage of it big time in chapter 13. It's just don't be too bothered by it. Okay? Block A does lose gravitational potential energy. It goes from a higher value of 0 to a lower value of negative something. All right. I shall continue here, because then the other side of the equation would be 1/2 m times the velocity of A squared and a 1/2 m times the velocity of B squared. That would be the kinetic energies after they have moved. The A block going down and the B block going up. Mm-hmm. And as we already pointed out, those are related in a 2-to-1 ratio. How about their gravitational potential energies? Well, let's look at A first. I would say it is an mg, and according to this, I would say it has gone down by r. So it is at a height of negative RA. Yeah.
Would you make one of those like just mv squared? Since velocity of A is equal to twice the velocity of B.
I will eventually. Yeah. Yeah. So I'm going to simplify it, but again, like a lot of these, I would suggest first just write out the equation, and then last solve the equation. Yeah. And so start with the basic principle and just write out the equation. And so, well, yeah, right now I have them separate, but you're right, I am going to put them together and get like terms out of them when I'm solving it. And likewise here, I would just write out what is the potential energy of block A, and I would also write out what is the potential energy of block B. So A went down by some number, and B went up by some number. Now I would start thinking more deeply about it and say, okay, let's start substituting in. Let's start solving this equation. And I guess what I would do first is to replace one of the A's or the B's with the speed of the other one. And since the problem says find the speed of A, I would substitute in for B so it's gone. And so I would have a 1/2 mva squared for the first one, and then the 1/2 m, and in place of B, I would put a negative 1/2 va and square it. And so I just do a direct substitution in there. And of course, then I have more math to do. But let's look about this side over here. I have an A and a B, but they describe the A and B in terms of H's. See, they say the total separation between them is H. All right, so I guess I got some more thinking to do here. I know they have a 2-to-1 ratio. That's fine. maybe put another way, the absolute value of A plus the absolute value of B is H, right? That's, I know one goes up and one goes down, but the total separation is H. And as we already said, the numerical value of A is twice the numerical value of B. And so, only thinking for a moment in terms of absolute value, I would say that is that description. Or, simplifying this, the absolute value of B is 1/3 H. So, that means that B is going up by 1/3 of H, which also then means A is going down 2/3 of H. And that seems to make sense, right? That's how you get a 2-to-1 ratio, right? A 2/3 coupled with a 1/3. The 2/3 is twice as big as the 1/3. The total is a whole. And so 2/3 and 1/3 make a whole there. All right. So knowing that, I could come over here and write this as an mg. And as this is saying, this is negative of the distance it went down. And of course, now we just see it went down by 2/3 H. And the other one went up 1/3 H. Now, and I think I have it. I still got some more math to do, but it looks like I've got a great equation that is going to give me a description of what is the speed of block A after there is a separation of H. And so maybe the first thing I would do is get rid of the m's. They're in every term. I would divide it through, no more m's. I then would combine my like terms, and I do have some like terms. This one is really a 1/2 and a 1/4, which makes a 1/8 VA squared. And this one over here is a 1/2 VA squared. Let me just get a common denominator of 8. So that's a 5/8, a half, which is 4/8, and another 8. And so that is 5/8 final speed squared. All right. Coming over to here, I can combine this. Let's see, this is a 1/3 GH, and it's a like term with a GH here, but that's a negative 2/3. So I will put a negative 1/3 GH there. And so once I move it to the other side, I get 1/3 GH is equal to 5/8 V squared. Simplifying this a little bit, I get an 8 and a 15. I get a GH. I take a square root and I get a VA. Ta-da! And so, again, notice then that I've, other than being a harder problem with the two objects, the different distances they moved, I'm just doing conservation of energy. Yeah. Which part? Here?
Yeah.
Okay, so this is just how far did it move down? Plus how far did it move up? No positive numbers, no negative number. I mean, all positive, no negative. They have to add to H, because they say when the total separation is H. Are you good with that? Okay, so then A is twice B. That was this discussion. You good with that? Okay. So now, a little bit of math just says, if I take a 2 and a 1 and add them together, I get a 3. Put the 3 on the other side, and I get 1/3 H.
Are those like terms? I thought that was 2 R and B.
Well, they are now that I put RB here. They started off as different terms, but then I did a substitution to get like terms, and then I can combine them together. Yeah. All right. Okay, well, let's go on. 15 is next on my list. This is, I think, a nice one to do because for the first time, we have some additional force outside of our springs and gravity. And so let's use this term. We really haven't really got a chance to discuss that term at all and to use it in our problems. And this one does do that. So letting me clear off the board here. And going to, whoops, I said 15, but I apologize, I skipped over 14. So let's do 14 first. 14 will allow us to do this term. So we haven't really done this term yet, so let's do that one. And 15, as I was getting to, is that term, and I haven't done that one yet either. And so 14 and 15 will be good examples, allowing us to see those in action. All right, so what did I say? Number 14. So 14 does have some friction in here. Here's what it says. It says a 2 kilogram block is attached to a spring with a spring constant of 500 newtons per meter as shown in figure 7.9. So that's a chapter ago. So I tried to call this up so that I would be ready to kind of show you the picture. It's not a surprising picture. Here is 9 right there, but it is just a spring and a block, and we can pull it to the left or compress it. Well, I guess pull it to the right or compress it to the left, and so we've got a whole energy discussion that they mentioned. So keeping that picture in the back of our mind, it says a 2 kilogram block is attached to a spring of spring constant 5 newtons as shown in figure 7.9. The block is pulled 5 centimeters. And you caught that right away, right? Watch the play on units there. Those are centimeters. So if we're going to do energy in joules, we want to make sure that our distance is in meters, right? A joule has a kilogram and a meter inside of it. Now they already gave me mass in kilograms, so I just quickly noticed that, but the 5 centimeters is important. It is pulled to the right of equilibrium and released. So that was the picture showing. Find the speed of the block as it passes back through equilibrium if A, the horizontal surface is frictionless, and if B, there is a coefficient of friction of 0.35. So that's what I was saying here to get us started. This is a good one to do this, although it doesn't show up till part B. So part A is the much easier one, but I think the author's having you do them because it'll give you some insight to part B. Part A would look something like this. You pull it over to the right. In fact, maybe I'll draw my own little picture. Here is equilibrium. Here's the wall. Here's the surface. So the spring has been pulled that way 5 centimeters. Now I'll go a little bit faster here. Let's see. How much initial kinetic energy does it have? Well, it clearly said it was pulled to the right, held there, and released from rest. So answer there is 0. How much gravitational potential energy does it have? Well, again, we can choose that number really to be anything we want based on what we choose y equals to be 0, but I see no point in calling it anything other than 0. It doesn't go up or down. And so whatever it has, the height is right now, call that y equals to 0, and it's going to stay that. So that one's a 0. Here's the only one that is relevant here for this problem, and that is we have pulled it so that we have a 1/2, and I forgot the value of the spring constant, 500 here. And the 500 is in units of newtons per meter. And so when it says I pull it 5 centimeters, I pull it so many meters, and then I square it. But I'm going to make sure I have that in meters so that my answer will be joules. In fact, I have more to do here, but just to get a number on the board and have kind of a discussion with it, I'll avoid my rule of saying write out the equation and then solve it. Here I'll start to write out the equation and start to solve it at the same time. But this is the, I'll call it the working energy. This is how much energy is stored in the system, and it's all because of that stretched spring that's been pulled 5 centimeters. Now, of course, A says where does it go? Well, that means the spring has pulled it back, and so it goes from here and it goes back to equilibrium. So at that point it is now moving. So it would be 1/2 times the mass, which in this case is the 2 kilograms, and some speed squared, but no other energies. There is no gravitational potential energy, as we said, and now the spring has got back to its natural length, so that one's 0. And in A anyways, there's no friction. And so of course, what's the difference then between A and B before we even solve A? Well, I guess I would still have in B the spring pulled 5 centimeters to the right. So I would still have the same working energy with or without friction to get you started. There's nothing different there. But of course, what is different is that when it gets back to equilibrium, yes, it's going to have this here for its kinetic energy. But what is importantly different here, and notably different, is that it is going to slide across the surface with friction, and that number is not going to be 0. And because of that, whatever number I get here for the speed must then come out to be a smaller number over here for speed, because some of the working energy ends up as heat, less for kinetic, and that means less speed. And so B will come out to be less speed. As I would have expected, it's got friction. I mean, we could have gone back to chapter 5 to say that. Of course, this is a much better problem, or I should say easier problem to solve with energy, because if I go all the way back to Newton's laws, then I've got a changing force. And a changing force means I have a changing acceleration. Now maybe I should say why I have a changing force. It's that spring again. And so if there's any way I can attack a problem with a spring involving energy, I would encourage you to do that. Because otherwise, you've got a non-constant force resulting in a non-constant acceleration, meaning to get speed, you're going to have to do an integral, and maybe even a hard integral at that. And so that's why energy comes so nice. All right, well, coming back to A then, I can pretty much solve this. This is pretty easy. They give me a 1/2 and a 2. And so this 0.62 is real simply the square root of all of that. And I'm getting a speed then of 0.79 meters per second for the speed in A. That would be the speed without any friction. Whereas over here, I've got a little more work to do. I still have the v squared, and the 1/2 and the 2 cancel off. But now I've got to know how much friction do I have. Well, this really brings us back to chapter 5. Free body diagram. Looking at the forces here, I have normal force pushing up. I have gravity force pulling it down. I've got the force from the spring pulling it left and right. And I've got friction pulling it left and right. Or maybe I should say, at least from this moment of release back to equilibrium, the force from the spring is definitely to my left, and therefore the force of friction is definitely to my right. Okay. That's the free body diagram. But what I also know from chapter 5 is that the force of kinetic friction is the coefficient of friction times the normal force. Then they were nice in this problem to give me the easy one. I should ask it again as we're getting ready for the test. Is the normal force always equal to the weight? No. And in the harder problems, certainly not. But I wouldn't call this one of the harder problems. In this one, you can kind of see that there is only an up and a downward force. And it doesn't move up or down. So the force up, which is the normal force, must equal the force down, which is the weight, mg. So I would say this case, then, the force of friction is just simply the coefficient times the weight. The weight is the normal force, this case. So coming over to here, I would have coefficient of friction times mg times distance traveled. And now I can begin to put in those numbers. They give me the numbers. What is the coefficient of friction for this one? 0.35. So this is 0.35. The mass is the 2 kilograms. G is the 9.8. Watch your distance traveled again. If it's going to move from here over to here, that is the 5 centimeters. So I will make sure I put it in my little formula here in terms of meters. And so that being said, I can go 0.625 minus 0.35 times 2 times 9.8 times 0.05 gives me a much smaller number in terms of the energy left for kinetic. And taking the square root of it gives me a reasonably smaller number for the speed. And so, not a surprise, it is a lower speed with the friction, with the heat. Yeah?
Could you explain the definition of normal force in words?
The normal force is the force from the surface. In this case, I'll call it a table. So here's the table. It is the force pushing up on the block. It may not just balance out its weight. Normal force does not equal weight. You might say it is in this case. And in many other cases. I could even do this. I could have put my hand on top of it and pushed down. And then I would have force pushing down. And then in that case, using your words, I would call the normal force as a force needed to balance both forces that are pushing it down. And so I would say in that case, the force pushing down from my hand on it, plus gravity pushing down, must equal normal force pushing up. Yeah, and then that would be one of many examples where weight does not equal gravity. We had other ones. You just take a block and put it on an incline. Then the normal force does not equal the weight of it. All those ones we had going in a circle, almost all of those, the normal force did not equal its weight. So there's lots of cases where normal force does not equal weight. The thing that is always true is Newton's second law, so write out the equation, solve the equation for the normal force. Good physical picture, free body diagram, write out the equation, solve the equation for the normal force. And just be logically sound as you work through the problem. Again, moving along, doing some different problems, maybe a little harder one, maybe a little easier, kind of depends. I kind of thinking maybe those were a little bit on the easy side, but they were ones involving friction that we hadn't done yet. Here's one, as I said, number 15 is a good example to do because it's one that involves this outside influence that we keep saying is there, and we haven't really had too much of that, and rightfully so. We're in the first chapter here, or second chapter, on conservation of energy. And we've done some really good forces. We've done gravitational forces, and we've done frictional forces, and we've done spring forces. That gives us enough to get started. But as our education continues, there are going to be other outside influence, and particularly next semester, where we get into forces from electricity, so electrical forces, and magnetism, so we get into magnetic forces. And so we're going to have to add on to that and have a discussion about those. But again, those are way in the future. Right now, this one I think just has some kind of influence from the outside by like a cable or a rope, something hooked to it. And so it says here, a crate of mass 10 kilograms is pulled up a rough incline with an initial speed of 1.5. Okay, so it's pulled up. They don't really say how it is pulled up. But drawing a picture might be very useful here in order to get an understanding. But here's that block, and I'll just put F for the fact that it is being pulled up. Actually, I don't know if it's parallel to the incline, but I think I remember reading this later on, and so let me keep going. Maybe my picture was a little too early, but I think they do tell me the direction of this force. The pull, well, there it is, next sentence, right? The pull of the force is 100 newtons, and it is parallel to the incline. All right, so I will put in my diagram that that's 100 newtons. Maybe I should also put that the initial speed is 1.5 meters per second. So it's already moving a little bit. And I'm kind of wondering, will this thing speed up or will this thing slow down here? So again, and maybe in my picture I should put the other things they told me so far, and that is the 10 kilograms. And they also said it was a rough surface. What's that telling me? Yeah, that there is going to be some friction. And so I'll need that term as well as this term. This is the outside influence, and then this is the friction. And so, okay, that's a big piece of this. A pulling force of 100 newtons is pulled parallel to the incline. It makes an angle of 20 degrees with the horizontal. The coefficient of friction is 0.4. It looks like I kind of drew my incline a little too much, but I'll put 20 degrees up there nonetheless. So the angle of 20 degrees with the horizontal, the coefficient is 0.4. And so mu sub k is 0.4. So again, that's going to be related to how much heat there is. The crate is then pulled 5 meters. All right, so we're going to pull it up, and eventually get to a position 5 meters further up the incline than what we started. And then we got a whole series of questions, which, in the interest of our time, we'll just kind of put them all together, because as you'll read, each of these 5 questions are really each of the 5 terms that are in our equation. Watch, it says, A, how much work is done by gravity? B, determine the increase of internal energy. That's the heat done by the friction. C, how much work is done by this external 100 Newton force on the crate? That's the additional force. D, what is the change in the kinetic energy of the crate? That's essentially what is the final speed of it, or that's really the last question. What is the final speed of the crate? And so I'm going to answer all of them together in one big swoop, A to E. What are the answers to all of those? And I think you'll begin to see it here. You'll see the first term, which is the initial kinetic energy. It is a 1/2 times 10 times the speed of 1.5 squared. I made that very clear, both the mass and the initial speed. The second one here, this is the initial potential energy, which, as we've been doing for the last 2 days, first question is, what is the initial height? Where do you want to call y equals to 0? Yeah, and again, I would say, why don't we call that starting point y equals to 0, which then makes that term 0. Great, I won't even put it in the equation. I will jump to this one. There's no springs involved, that's 0. I'll jump to the new one. And fortunately, it was an easy one. Well, let's do this integral again. Work from the outside. They say it is a force of 100. All right, I'm going to put in my force. I'm going to do the dot product. Remember, the dot product was the magnitude of the first times the magnitude of the second times the cosine of the angle between them. So what is the angle between them? Maybe it begs the question, what is them? The angle between them. Well, what's them? It's the two vectors you're taking the dot product with, right? It has nothing to do with the slope of the incline. And I'll be tempting to put cosine of 20 degrees. That's not what that meant in here, right? This is the dot product between these two vectors. So which way is the force? Along the incline. What direction does it move? Along the incline. So what's the angle between them? 0. Yeah, that's easy. Because what's cosine of 0? 1. And so what I guess I get is 100 newtons times an integral of dr. Well, I couldn't ask for an easier integral than that. And again, that's not what the problem's about. The problem's not about doing a hard integral. I know you will get plenty of hard integrals in your Math 160 class, so good luck on those, by the way. But that being said, this is not a hard integral. This is more about reading and understanding the physics behind that integral. And so we're just going to get 100 newtons times the distance it moved, which is 5 meters. And so that's what I'm going to put up here. The energy added from this outside influence looks like it's going to come out to be 500 joules of energy. Ooh, which was one of the questions in there. How much work was done by this outside influence? I think that was question C or something like that. But now let's go over here to the other side here. Right here. What is the speed at the end of this motion, this 5 meters? Well, that part I don't know. I do know its mass is 100, but its final speed is unknown to me. In fact, that is the ultimate question at the end of this. E, what is the final speed? If I can get all the other terms, which is questions A through D, answered, I can then answer E, what is that final speed? So there is really the main term of the equation. This is a fun one here. What is the gravitational potential energy? Well, its mass is 10. G is 9.8. What is its final position? Good. You guys, it's now 5, is it? It went up the incline 5. But that's not what y means. Y means how much higher is it vertically? And so wouldn't that be 5 meters multiplied by the sine of 20 degrees? So see how we need the sine of 20 degrees here, but we don't need it here. Easy to confuse those. That's, again, why it makes a good example to work those out. Next term, well, there are no springs involved, so I got nothing to worry there. Ah, the heat. There is heat this time, right? In fact, kind of looking at the whole point of this problem, I think the author is trying to say here is we have an initial speed. And if we didn't have something pulling on it, we would have seen that that energy went into making it go higher and heat. And because of that, the block would go slower by the time it got to the 5 meters. Fair enough? But we are actually then pushing on the block. The question is, are we pushing it enough? Will this final speed right here come out to be more than 1.5? Meaning we did more than enough work by pushing on it to compensate for the fact that we've got to lift it up and we've got to create heat? Or did we not push it enough and so the final speed is lower than 1.5? It's going to be interesting here to find out what this final number is. Did the block speed up or did it not speed up? And this is going to be the magical factor. How big does that number compare to really these next two? Because this is how much has to go into gravitational energy. And this one right here is how much heat is created, which again was one of those questions up there. How much heat is then created? And of course, now we've got to talk about what is the frictional force. And again, this is where the free body diagram comes back into play. And like we did on that last problem, the free body diagram, looking something like this, means that we would have a normal force off at an angle. We would have a frictional force down the hill. We have this force from my hand pulling it up the hill. And gravity still going straight down. Doesn't matter the fact that it is tilted on an incline, gravity is still straight down. And so in order to get the amount of friction, we need to know the normal force. And here is a good example of what you were asking about. This normal force will not be equal to the weight. And in fact, if I make an axis that is tilted, something like this, and I add up all the forces in the y direction and realize it does not move in the y direction. It moves up and down the incline in the x direction. Then I will get a normal force pushing up. These two don't have anything in the y direction, but that one sure does. Right? It's that piece of it is in the y direction. And so it would be nice to know this angle in here, which maybe I need to get that back here. I'll draw a vertical line. And then I will draw a line perpendicular to the surface. But if that angle is 20, that's going to make that angle 70, which is going to make that angle 20 again. Okay, so this angle should be 20. So the amount of the gravitational force into the surface of the incline is mg cosine 20. Which again gives me to what I need to know here. What is the normal force? And so now once I know the normal force together with the coefficient and the distance it moved, I can actually fill this in. Let me put above it, right? This is the coefficient of friction times the normal force times the distance it moved. So in my case it's 0.4. Whoops, and for some reason I changed colors there. But it's 0.4. The mass is the 10. G is 9.8, cosine of 20 degrees, and distance is 5 meters. So there are all the factors to answer one of these questions in here, which was determine the increase of internal energy of the crate. The change in kinetic energy would basically be everything but these two terms put together. This would be initial, this would be final. And so if I put that one together with that one together with that one, that would be the change in kinetic energy. But for me, let's go right to the end. What is the final speed? And so I'm going to take this first term, which is 1/2 times 10 times 1.5 and square it. I'm going to add to it 500. I'm going to subtract 10 times 9.8 times 5 times sine of 20. From there I will subtract 0.4 times 10 times 9.8 times cosine of 20 times 5. And so there, I've got a 160. I will divide that by a 5. And when it's all said and done, I get a speed of 5.65 meters per second. So I did a lot of calculations there. Probably should have broken it into a couple of pieces. I guess that's why they asked A through E. During the test, I wouldn't encourage you to do that many calculations there in one step on your calculator so that you don't make a mistake along the way. But assuming I didn't make a mistake, then this is the speed. And then notice it is going faster than it started. So notice then that the work done by the outside was more than the energy went to lifting it up, gravity, and the heat that was created. And because of that, the extra energy then gave it an acceleration up the hill, and so this thing is going faster and faster and faster. Yeah.
So if we change the angle of the pull, would it be easier or would the answer change?
Well, the answer would have changed. I would assume what you mean by the angle of the pull, that maybe you're doing something like that.
Yeah, reducing the normal pitch.
Yeah. And so there's a couple things that would happen there. One would be back here at this calculation, I would have a different number. So this number would go down. However, as you are pointing out, this number would also go down because the amount of friction is related to the normal force. So how do those two compare would need to be decided before I could say that's going to change the speed here. Yeah, yeah. So. And I don't think there's one answer. I think if I pull too much like this, I think this one goes down so much that I am going to get a lower speed. Yeah. Mm-hmm. Even though this one would be going down. Yeah. Yeah. Okay. Well, I hope those were good ones. I'm going to keep going. I think 23 is a real challenging one, especially question B, and I think it's B in the middle of this one. It's going to make you think, which is the whole point in all of these problems, so that you will be that much better of a thinker, and you will be able to work on some problem involving engineering of some type and design. Maybe it's build a newer or bigger building, or maybe it's designed new drones. There's a new marketplace, $1 billion of building drones, flying drones, fixing drones, improving drones, programming drones. You know, what is going to happen? And so what decisions do you need to make? That's this whole critical thinking process here. All right, so going on with our deductive reasoning, our critical thinking, what leads to what, and so forth here. Let's try number 23. And again, this will really ask you to put some things together here. All right, it starts here. It says a toy cannon. It uses a spring to project a 5.3 gram soft rubber ball. Now, let me pause right there. Grams, right? Energy is in newtons. I'm sorry, energy is in joules, and inside of joule is a newton. And inside of a newton is both a kilogram and a meter. So for this to work, I need things in kilograms. All right. The spring is originally compressed 5 centimeters. So it has a force constant of 8 newtons per meter. Well, there's our normal unit, so that's good. When the cannonball is fired, it's going to move 15 centimeters through a horizontal. I'm glad they said horizontal, so I know that I'm really not dealing with gravity here. A horizontal barrel in the cannon. And the barrel exerts a constant frictional force of 0.032 newtons. So they just tell me what the force is straight out. So this is a little easier in that sense than the other ones. I don't need to worry about what's the coefficient of friction and what's the normal force here. They've put all those together and say, this is the frictional force. Now, I need to go from frictional force to heat energy, but they've at least given me the frictional force. A, what speed does the ball, with what speed does the projectile leave the barrel of the cannon? All right. I'll just start there. Here's A. Now, I'll even come over here and say, all right, if that's A, then what does the picture look like? And so, helping me solve this problem, I guess I would say, all right, well, here's what I have. I have a little ball. There's a spring. If I read it correctly, they say that they are going to push back and compress the spring 5 centimeters. From that, this so-called cannon is horizontal. And so the ball is starting back here. But here's a really important part that I got to make sure I catch this in the reading. It shoots, does it just travel 5 centimeters? No, it said that the projectile travels then 15 centimeters before it gets to the end. So the spring does not go all the way to the end. There's 2 different distances involved here, one involving the spring and one involving the barrel. And don't miss that, because obviously everything we do beyond that totally gets fouled up if we try to apply our equations and develop our equations based upon the wrong physical picture. And so we've got to have that physical picture matching the equation. So the toy cannon does shoot this 5.3 gram soft rubber ball. The spring is compressed 5 centimeters and the force constant is 8 newtons per meter. I didn't put that at all in my figure here, but there is the spring constant. And I compress it. When the cannon is fired, the ball moves 15 centimeters through the horizontal barrel of the cannon. And the barrel exerts a constant force of 0.032. In fact, maybe I'll put that up here, that the force as it slides along is 0.032 newtons. Okay. So I think I have everything in there, and now I'm ready to answer this. What is the speed of the projectile when it leaves the barrel of the cannon? But as you've been seeing for the last 2 days, I've been using this. I'll continue to use this. We'll, I guess, continue to use it till the time's up. We won't even get started in Chapter 9, but, you know, this is hopefully getting more and more familiar with you. I would start off and say, what's my initial speed? 0. 0 kinetic energy, nothing to write there. What's my initial gravitational energy? Well, depends where you want it, y equal to 0. I would put it at the height of the cannonball, which doesn't go up or down, so there's a 0 here and a 0 there. What is the initial energy of the spring? Well, there it is compressed. And I must use the definition of x equaling 0, the natural length of the spring. And so it has been compressed 5 centimeters. And to compress it with 5 centimeters, I will change that to meters so that I'm working in units of joules. I will also ask the question and decide for you guys, which way do you want to call positive or negative for the compressed spring? It wouldn't matter, of course, mathematically. I see some of you indicating that, well, you're moving it to the left, which is normally the negative direction. Okay, it is normally. Then I'll stick to it and put a negative in there. But I would say that is the left-hand side of this equation. There is no other forces that are different than that one, or different than what aren't already covered in these equations. This one is the one I'm after. What is the speed of it? So there's the 1/2, the 0.0053 is the mass in kilograms. They gave me the 5 grams, 5.3 grams. So I'm going to change that to kilograms so that I can then say this then is the final speed squared. That's what I'd like to find. But of course there's more to it. For example, we get over to here, which we already said is 0. We get over to here, the spring now has stretched back to its natural length and the cannonball has moved on, so that one is 0. But of course this one does have a number. This is a force of friction. That force of friction is 0.032 newtons. And how much distance do I have? Is it 5 or 15? 15. So the friction is for the whole 15 centimeters. And then knowing that, it's a matter of plugging and chugging into here and coming up with what do I get then for the speed. So the 1/2 times the 8 times the 0.05 squared is the energy I start with. Some of that right here, the 0.032 times 0.15 goes away as heat. Once I have that, I can multiply by 2. Then I can divide by 0.0053. I can then take the square root of all of that, coming up with a speed of 1.4 meters per second. And so there would be the first part of the answer. What is the speed as it exits the barrel? But I like how this one goes on. It's got some other creative questions here. At what point does the ball have the maximum speed? So is the maximum speed when it exits the barrel? No. Most of you are shaking your head no. Why not? Yeah, that friction, right? I mean, the spring only pushed it 5 centimeters, right? Didn't it travel another 10 centimeters throughout where there was friction and it was slowing down? All right. So if I'm hearing you right, you're saying it is not at the end of the barrel. So where is it?
When it leaves the spring.
Is it when it leaves the spring?
Yes.
No. Why not?
Is it past the maximum potential of the spring? Right after energy.
Shall we take a moment and look at the free body diagram? I mean, here's this little cannonball. What forces are on this cannonball? It kind of does depend on where it's at, fair enough. If the spring's still pushing on it, there's a force from the spring to the right, right? Or correct? And if it's already left the spring, that one's not there. Okay, so keep in mind that one may or may not be there depending on where the cannonball is. I would say then there is a frictional force in that direction. I would say there is some kind of normal force and some kind of mg. I think that covers all the forces there, and this one may or may not be there. But let's just look at the horizontal forces for a moment. Since my question is what is its maximum speed, I guess this one and this one is not really my focus. When will this object be accelerating, going faster, and accelerating, going slower? And if it helps, I'll use the word deceleration, albeit we don't like that word deacceleration. It kind of takes away from, but anyways, our numbers. So when would this object be accelerating and when would it be deaccelerating? Yeah.
It'd be accelerating while it's being pushed by the spring?
Always when it's pushed by the spring?
When is the frictional force is more than the
Ah, and I would say, and this is what I want you to notice, I would say it is only accelerating so long as the force from the spring is greater than the force of friction. You see that? So as the spring pushes, doesn't the amount of force from the spring change? I mean, when we begin the process, the spring is pushed all the way back, and there is a huge force on it. There is a force from the spring much greater than the force of friction, and it accelerates, 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 accelerates. But the very last part of the spring, isn't this force zero or near zero? So even though it's still in contact with the spring, isn't this greater than that one? And so I would say that at some point, and I'm not sure where that point is, which is why the question made a good question in my mind, is sometime before it gets back to the 5 centimeters, and I'll just put a line right there. At that point, the force from the spring may be equal to the force of friction. And that's where acceleration changes to deceleration. So why don't we solve that? What point? At what point does the force from the spring equal the force of friction? We know the force from the spring is a K, which is 8, times X. And we know the force of friction is 0.032. And maybe I should emphasize that I have, of course, dealt with the absolute value of this spring. So I completely ignored the negative sign in Hooke's law. And so X is 0.004 meters, or 0.4 centimeters. Ah, that's what I was looking for. So it is close back to the natural length of the spring, but not quite there. This distance right there is 0.4 centimeters. And that is the point that the ball has its maximum speed. Everywhere back here, the force from the spring is more than friction, and therefore it goes faster, 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 faster. As it's getting close, the force from the spring is just barely greater than the force of friction. But it still is, and it still goes just a hair faster. But when it gets right here, even though it's still in contact with the spring, and even though the spring is still pushing it, the spring's force has gone down so low that the force from the spring is now less than the force of friction. And it is no longer accelerating. So that is the point that I have the most speed to this ball, right there. At what point does the ball have its maximum speed? And see then, what is this maximum speed? So I can't really solve for what the maximum speed is, of course, until I figure out where the maximum speed is, and that's why they asked me B. And so now I can go on to C and say, okay, well, what is that maximum speed? And so let's do the same thing that we did in A, except this time we're not going to let the cannonball go all the way to the end of the barrel. This time we are going to let it just move to this point right here, where the force of the spring and the force of friction are the same, and so, well, what is its speed at that? And hopefully we'll get a number greater than 1.4. So let's start again here. I would say it starts at rest. I would say there is no gravitational potential energy, but there is energy stored in the spring. So just like we did in A, I'm going to write a 1/2 times an 8 times a 0.05 squared. That's the same. Nothing different there. And then, as it gets to this magical point where it has its highest speed, I would have the equation for the kinetic energy, which would be the 1/2 0.0053 V final squared. So that's the same equation, if you will, but of course the number for the final speed should be a little bit bigger. And why it should be a little bit bigger is really right here. Don't we have less heat generated? And what else? We still have energy stored in the spring, right? The spring is not completely returned at that point. That was this whole argument. And so I should have a 1/2 8 times the distance that the spring is compressed at that point. And as we just worked out here, this is the distance it is compressed. Now, not much, which kind of makes sense. It shouldn't be much because we're getting our energy from the spring. You would have kind of expected to be giving it out. But the point is here that there's a trade-off between stretching out the spring and going the distance because of heat. And that's what this argument was all about. So that would be a term involving not just heat, but where is the spring? The heat then would be 0.032, there's the force, times what distance? Zero, 0.046. Oh, no. Too many zeros. 4, 6. Why that number? Question?
I know that it's negligible since it is squared, but would that 0.204 be negative?
Oh, well, I guess it would be the same as this one.
But isn't that one?
Which I guess earlier we called that negative, right?
Yeah.
Okay, so negative, yeah, okay. To be consistent with how we defined it before. Okay. So without changing our definition, I'll put them both negative. Oh, but back to this question, where did this come from? That's how far it moved, exactly. It was way back here. And had it gone all the way to equilibrium, then it would have gone 5 centimeters. But we're trying to say it's shy of 5 centimeters by 0.04. Question? Oh, shoot, thank you. No, I'm still back. Yeah. I'm still back there. And so now that we're out of time, we can finish this problem by saying, well, what is this maximum speed here? And so I guess I will start with that one again. 1/2 times 8 times 0.05 squared. That's this first term. I will subtract off this term, which is 1/2 times 8 times 0.004 squared. I will also subtract off this term, 0.032 times 0.046. And that just leaves me with this, which is times 2 divided by 0.0053. I will take the square root of all of that, and it looks like a 1.78 meters per second is then the speed, and it is definitely bigger than that one. Great. And that was the whole idea. Well, I'm hoping those were very, very helpful. There was even more that I would have liked to do. There never is enough time to do all of them. But work on those. Obviously, you have a test coming up on Monday. I forgot to mention that you have a review here on Saturday with Dawn, and so I would put that into your schedule. I'll mention it again on Wednesday. We'll go into lab today to do some more